Let's take a look at the A-level further statistics paper from June 2022. We're going to start from question 1. In this question, we're told that a researcher is investigating the number of female cubs present in a litter of size 4. He believes that the number of female cubs in a litter can be modeled by the binomial distribution with parameters 4 and 0.5, which means that he thinks there's a 50% chance that each cub in the litter would be female and 50% chance that the cub would not be female. He randomly selects 100 litters, each of size 4, and records the number of female cubs. The results are recorded in the table below. So that's the first table that we see in the question. And he calculated the expected frequencies as follows. So we've got some missing values, R and S, and we're asked in part A to find out the values of R and S. Let's look at part A first together. This is the first question in the paper, so normally it's quite straightforward, and it is. Part A simply asking us to find the expected frequency out of 100 litters, where X is the number of female cubs. It's assumed to have binomial distribution with parameters 4 and 0.5. So R is simply 100 times the probability that X equals 1. And by symmetry, it's exactly the same as the expected frequency when X equals 3. X is expected to follow a binomial distribution, so we can work out the probability of X equals 1 using the probability for binomial distribution. So X equals 1, that's 4, choose 1, and that's how we work that out, and R equals 25. Similarly for S, there are two ways to work out S, because we know that the total number needs to be 100. One easier way to work that out would be to say 6.25 plus R plus S plus R plus 6.25 equals 100, and we know that R is 25, and therefore S has got to be 37.5. But let's check that independently using the binomial distribution as well. Very similar to R, S can be worked out by the 100 times probability of X equals 2. X equals 2 could be modeled by 4, choose 2, 0.5 squared times 0.5 squared. And we do get 37.5. So these are the two ways to work out S. So that's our part A. Let's move on to part B. And remember that for R, we had 25. For S, is 37.5 and 25 there. So part B, it says carry out a suitable test at the 5% level of significance to determine whether or not the number of female cubs in the litter can be modeled by the binomial distribution parameters 4 and 0.5. We're asked to clearly state our hypotheses and the critical value used. So let's make sure that we answer these questions. So that's important for us to state the hypotheses and also mention the critical value. Part B, let's state our hypothesis first. In our part A, we defined X to be number of females in a cup. So what we can do now is we can say that H naught, which is the null hypothesis, we can say that X follows a binomial distribution of parameters 4 and 0.5. Basically, binomial distribution is suitable. And H1, the alternative hypothesis is simply that binomial for 0.5 is not suitable. And now we need to work out test statistic. You may remember this formula, observed value minus expected value all squared over expected value, and the sum of all of those, which could also be simplified into this formula. And for me, this formula is a much easier formula to use, so I'm going to use this. I'm going to write in this table the different values. So I could be 0, 1, 2, 3, 4. Observe the values. So that's this table here. 10, 33, 33, 15, and 9. And for expected values, 6.25, 25, 37.5, 25, and 6.25, making use of the R and S values that we worked out in part A. And before we work out the values of O squared over E, let's double check that there are no expected values that are under 5. It's great because the lowest value is 6.25, so none of the values are under 5. So each of the column could be a standalone observation and none of them need to be combined. So let's work out O squared over E. So that's 100 over 6.25. This is 16. 33 squared over 25 is 43.56. 33 squared over 37.5 is 29.04. And then this is 15 squared over 25 gives us 9. 9 squared over 6.25 is 12.96. Great. And the sum of all of these values minus n equals, so 16 plus 43.56 plus 29.04 plus 9 plus 12.96 minus 100 gives us 110.56 minus 100, which is 10.56. Let's compare that to the critical value. So the critical value, let's write that down because the question is asking for this. Critical value is chi-square distribution, 5% significance level. And let's work out the degree of freedom. Degree of freedom, there are 5 columns, 1 constraint, so the degree of freedom is 4. Let's take a look at the statistics table. This is where we see percentage points of the chi-square distribution. We're interested in a degree of freedom of 4. Significance level of 5%, and therefore the critical value is 9.488. So the critical value is 9.488. And because the critical value is less than our test statistic, therefore there is evidence to reject H0 because the difference between the observed values and the expected values are too big, much bigger than the critical value that allows us to accept. So B for 0.5, not suitable. And that's our conclusion for part B.